By now, hopefully you have the idea of how to do anti-differentiation by substitution. A lot of this is just going to be examples showing you how to break things apart, why the U is what it is, and kind of how to tell different situations apart. So we're working on choosing the appropriate U for the U substitution. Hopefully you can already evaluate indefinite integrals using substitution. I'm going to show you a couple examples of definite integrals. And something else we're going to try to be working on, because eventually you have to decide, is identifying when anti-differentiation by substitution should be used. And it's generally chain rule, but you're going to see today it's not quite as obvious sometimes. And I'm going to keep hammering this. Instead of modifying what du is equal to, we always want to modify the original integral. Because, well, let's go back. If you are modifying the integral, multiplying by 5 over 5, hey, that's all good. But a lot of times, and I've seen it, somebody asked me just today after we had this lesson, can I do this? I'm like, no, that's actually the thing I'm trying to get you to not do. We'll see this in a moment. But the big error, when you are doing a definite integral and you do U substitution, the original bounds are x's. So we need to change those original bounds of integration from x values into U values, which isn't terribly difficult. You just have to remember to do it. So how do you evaluate the indefinite integral of secant squared x times tangent x dx? And the answer is we actually have a couple of options. With substitution, what we see is, most people pick out that U is tangent of x, which makes du secant squared x dx. And, tangent of x, that's going to turn into U, so we're going to rewrite that as the integral of U. And then everything else, the secant squared x and the dx, all of that combines to be du. And so antiderivative is 1/2 U squared plus a constant, so 1/2 of tangent squared x plus a constant. But the thing is, you may not have realized, I'm just going to erase all this. U could also be secant of x. In that case, you get du is secant x tangent x dx. And again, we get, weirdly, the same indefinite integral of U du, the same antiderivative, U squared over 2 plus a constant, and the same, well, I guess that's different, huh? Secant squared x over 2 plus a constant. So side by side, I don't know, this really bothers me. It doesn't really seem right that secant squared over 2 and tangent squared over 2 should be equal. And of course they're not equal, but they do have the same rate of change. You can verify that. But the difference is really this c, and you have to think for a second, but it's just that these c's are not equal to each other. So kind of weird it works out. If you don't believe me, graph both secant squared x over 2 and tangent squared x over 2, and you'll see they're the exact same shape curve. They have the exact same derivative or instantaneous rate of change everywhere, just one is higher than the other. So you could add 1/2 or subtract 1/2 to move things around. Okay. So let's think about this. Eventually you have to decide, if I'm going to integrate tangent, I have to use U substitution. But today it's kind of a given. Now, one thing U is not is tangent of x, because that would make du secant squared x dx. And if we use tangent for our, that's going to become a U. The only thing left is a dx. And, this is the exact thing, people think they can divide. No. That's the thing I'm telling you not to do. Don't divide. If you don't have, in this case, secant squared x, let's say that another way. Well, if I wanted du, then I need a secant squared x dx, and we don't have that, which means, one of two things. Either this is not U substitution, or you chose the wrong U. And it turns out you chose the wrong U. Let's try another U. Maybe it's U is equal to x. That would mean du is dx. Well, that's actually pretty good. So we get the indefinite integral of tangent of U du, which is allowed, but it's not very helpful because we haven't exposed any structure. So What you really need to do is find, this piece has its derivative somewhere else. And once it comes to you that tangent is sine of x over cosine of x, then you realize, oh, I get it. The derivative of sine is cosine. The derivative of cosine is negative sine. Can you tell which one is u? Is u going to be sine or cosine? And the answer is cosine. And the reason is really in the du, not in the u. So if du is negative sine of x dx, and we do need a negative, so I'll just pop those in, you kind of have to think ahead. Before you've decided that u is cosine of x, you have to know du is the thing that's multiplied by dx. So the derivative of cosine is sine. That's the thing that's multiplied by dx. So we kind of work backwards. Oh, I guess u is cosine of x. Anyway, so the negative out front comes down. The integral comes down. The sine of x and dx become du. And that means we have blank over cosine, so we'll just do 1 over cosine. Antiderivative of 1 over u is natural log of the absolute value of u. So we get negative natural log of the absolute value of u plus c, or negative natural log of the absolute value of cosine plus c. And you can check by taking the derivative, and we don't worry about this absolute value on the cosine here, but you can see that checks out. So what are we going to do to find the antiderivative of cotangent of x dx? Well, again, u is not x, u can't be cotangent. Oh, wait, cotangent is cosine over sine. So we'll do that. And hopefully you can tell that the derivative of cosine is sine, but that sine isn't multiplied by dx. So similar to the last problem, we're going to say u is sine, the thing in the denominator, because du is cosine of x dx, that thing in the numerator. So we get a much cleaner 1 over u instead of 1 over sine, and cosine of x and dx become du. Antiderivative of 1 over u is natural log of the absolute value of u plus a constant, and then just put sine of x back in for u. Okay. So now let's do a definite integral. We call this change of variable because weirdly we're going to change the variables. And then we'll evaluate everything. And so we already saw that u could be tangent of x. And then du is secant squared x. And u could be secant x. And du is secant x tangent x. But because we have bounds of integration, we're going to evaluate tangent or secant at those bounds. So you have to choose which one you think you're better at. I'm better at tangent, so I'm going to choose tangent, which makes du secant squared x dx. But let's see. I'll leave the bounds off for a second, and that's u du inside. Tangent became u, secant squared x dx became du. You have to remember this 0 right here, that's x equals 0. That pi thirds is x equals pi thirds. If we write something as a bound of integration down here, those need to be u's. So what we need is something that converts x's into u's, and that is tangent. Because that says the u value is tangent of the x value. So we're going to take 0, put it in here. Tangent of 0 is 0, and we put that down here for the lower bound of integration. And then tangent of pi thirds is square root of 3 over 2. And so, over 1/2. So tangent of pi thirds is square root of 3. Now the cool part with changing variables is you don't have to change back to x's. We just do the antiderivative of u squared over 2 from 0 to root 3. U equals 0 to u equals root 3. And then we substitute in. Square root of 3 squared is 3 over 2 minus 0 over 2. Cool. So what about the definite integral from 2 to 5 of 2x times the quantity of x squared plus 1 to the 4th dx? Well, hopefully you're getting to the point now where you see that x squared plus 1 That's going to be u, and its derivative, 2x, is way out here with dx. So this is a nice, easy, straightforward substitution. And so we're going to rewrite that integral instead of x squared plus 1 to the fourth, u to the fourth, and the 2x and dx become du. So we can't put 2 down here, because that's x equals 2. So we put 2 into our converter. U is 2 squared plus 1, so 5. And the upper bound is 5 squared plus 1, so 26. And then antiderivative shouldn't be a big deal. 1/5 u to the fifth, from u equals 5 to u equals 26. Substitute in 26 and 5 and realize 26 is insane. Don't worry about simplifying that. That's just crazy. All right, what about dx over cosine squared of 2x? What kind of substitution are we going to do there? Well, again, is u cosine of, doesn't really matter whether it's x or 2x, can u be cosine of anything? Well, no, because, there's no sign in the numerator up here. So we know that's not going to work out. And for the same reason, u can't be cosine squared. So turns out you have to just think for a moment and realize, let's rearrange. 1 over cosine, the reciprocal of cosine, is secant squared. So this is just a memorized derivative rule, right? That's the derivative of tangent. So we're going to say u is 2x, du is 2dx, and I know you can counteract that, but we're building a process skill here where we're getting used to just changing the integral. So in order to get a du, I want a 2dx, so I'll just multiply by 2 and 1/2. So now I have a 2, I have a dx. I can turn that into a du. Obviously, this 1/2 out front comes down, and we haven't done our integral yet. And so 1/2 tangent of u plus a constant, and replace that u inside a tangent with a 2x. Ooh, now we get into more and more stuff. 1 over x squared plus 4 doesn't really feel like something you know. And then, you're like, what the heck is going on? It's not something I've memorized. U can't be, doesn't really look like anything we have. U can't be x squared or x squared plus 4, because that would give us a 2x dx, which we can create a 2, we can't create the x. So what do you do? And the answer is you kind of realize, if that was x squared plus 1, that kind of looks like the derivative of inverse tangent, which it is. So we have to factor out that 4. And you can see 4 times x squared over 4 is x squared. That worked out. 4 times 1 is that 4. But we need to rearrange a little bit more because, I don't know, the way I'm thinking of it, the derivative of inverse tangent of stuff is 1 over stuff squared plus 1. And so we need to rewrite that x squared over 4 as just, one thing squared. And so now you can see, I brought that 4 up front. Now you can see that u is going to be x over 2, which it doesn't look like at all from the beginning. And du is 1/2 dx. Now we don't really have a 1/2, but that 1/4 is a 1/2 times another 1/2. Maybe we'll bring 1 inside here. And now we have that 1/2 dx that we need. So one of the 1/2s is left over out front. 1 over stuff squared plus 1 becomes 1 over u squared plus 1. And our 1/2 dx becomes du. So we get an antiderivative of 1/2 inverse tangent of u plus c. So 1/2 inverse tangent of x halves plus c. Okay, moving on. And, you can probably guess that this is similar, and it is. Again, we see right away, u can't be 4 minus x squared because there's no x in the numerator. So we realize, that kind of looks like inverse sine. And so we're going to factor that 4 out. 4 times 1 is that 4 we started with. 4 times x squared over 4. My kids made fun of me all day for that. 4, it looks ugly. 4 times x squared over 4 is x squared. And again, we want stuff squared inside that square root. So 1 minus x over 2 all squared. And then u is going to be x halves. Du is 1/2 dx. And again, we need a 1/2 and a dx. And in this case, we have that just in a slightly different form. So we're going to say the integral. Oh, that's super weird. How come that's happening? The integral of 1 over the square root of 1 minus u squared du has an antiderivative of inverse sine of u plus a constant, which is inverse sine of x halves plus a constant. All right. What about the indefinite integral of x over x squared plus 1 dx? This is the one, I don't know, you've been waiting for. Where that x squared plus 1 in the denominator, that actually is the u. And we can tell because its derivative is, well, maybe not is, but involves x times dx. Because we can always create a 2, which we're going to do now. We're going to make a 2x, so we can make an exact substitution, multiplying by 2 and 1/2. And so the 1/2 comes down, 2x and dx become our du. So we end up with 1 over u, which has an antiderivative of natural log of the absolute value of u. Bring down the 1/2, and don't forget your plus c. And notice here at the end, 1/2 natural log of x squared plus 1 plus c. We actually drop the absolute value. You can keep it, but x squared plus 1 is already 1 or greater, so the absolute value is just redundant. I don't know. I really like this example just because it pulls a lot of things together, a couple of which I'm going to show you afterwards. And that is, what the heck do you do? The first thing is maybe u is cosine of x. That would make du sine of x dx, which is not possible, or at least not likely, because that sine is locked up in the denominator and inside a square root. So maybe du. Maybe du is cosine of x, which would make u sine of x. And if u is sine of x, well, then we can have 1 over the square root of u, and we can have a du, but we had cosine cubed. Ooh, forgot a dx. We had cosine cubed, and, well, I guess there's cosine squared left over. Well, what the heck do I do there? Well, again, you're not going to rearrange du. We're always going to rearrange the integral. And so let me delete this. And what we're going to do is break that cosine cubed into cosine squared, and cosine squared using a Pythagorean identity is 1 minus sine squared. And now, if we make our substitutions, u is definitely sine of x. So we get 1, well, 1 is 1. Sine squared becomes u squared, square root of sine of square root of u, and that extra cosine that we popped off with the dx becomes du. But you might be thinking you still can't integrate. You're kind of right, because that's a quotient. So we're going to do 1 over the square root of u gives us u to the negative 1/2. U squared over root u is u to the 3/2. Those we can take antiderivatives of. Antiderivative of u to the negative 1/2 is u to the 1/2 with a 2 out front. Add 1 to the exponent here, and we get u to the 5/2 with a 2/5 out front plus c, and just resubstitute and put some radicals there. So 2u to the 1/2 is 2 square root sine minus 2/5 times the square root of sine of x raised to the 5th power plus a constant. So, oh my God, these are getting worse and worse. What about sine to the 5th power? Well, you got a hint of it on the last one. And the hint was, basically that there's going to be a sine of x dx here at the end, which means u has to be cosine of x. And if u is cosine of x, I guess we need some cosines. So we're going to get cosines by breaking off even powers of sine squared and sine squared times an extra sine. And each of those sine squareds we can replace with 1 minus cosine squared. So then you can see u is cosine of x, du is negative sine of x dx, and I'm going to put a negative out in front here, 2 of them. And let's see, what do we get? Well, the one negative comes down, the other negative gets used up to make a du, and 1 minus u squared times another 1 minus u squared. And we don't really want to deal with anything, so we just multiply everything out. 1 minus 2u squared plus u to the fourth du has an antiderivative. And I just put the negative out front so I don't have to worry about distributing in my head. So I'll do that later. Antiderivative of 1 is u. Antiderivative of u squared is u cubed over 3, so 2/3 u cubed. Antiderivative of u to the fourth is u to the fifth over 5, and u nu plus c. By the way, you could have a minus c there too if you wanted. You just have to make sure when you create an extra constant, it keeps its value. So we'll go ahead and substitute cosine in, and we're nearly done. This is kind of a weird one that doesn't show up, so I think I'm going to leave that and go play with my kids.